Hello, welcome to flipped learning mode of KLU. In this particular session, we are going to talk about the algorithms that we have been dealing with for quite a few sessions. In this case, I would like to throw a question to you. Have you ever wondered why some algorithms work brilliantly while some algorithms take hell amount of time? Well, the answer remains inside this particular session. You will be discovering why this is happening, and that is what our discussion is, that is complexity theory, and this is the part 1. We will have a part 2. So let us begin our journey towards this complexity theory. Okay, so in this particular session I am going to introduce you the complexity theory, and you will be able to measure the time and space complexity for an algorithm, and we have to understand the fundamentals of complexity theory. We will also know about asymptotic notations, and as well as we will analyze the time complexity of a Turing machine. At the end of this session, you will be able to understand the fundamental concepts in terms of time and space, and explore the limits of algorithm solvability and decidability. These are the different aims of this session: instructional objective and learning outcomes. Well, even when a particular problem is decidable, what do we mean by that? Generally, what happens whenever a problem is there, we try to find out a solution, and if the solution is available at our hand, then we just try to implement that. Now, here the solution is in the form of a Turing machine. So that means we have a problem and we have a solution in the form of a Turing machine. Now, when we say a problem is decidable, in this case, whenever a Turing machine runs, it has got 3 different outcomes. Either it will accept and halt, reject and halt, or loop and doesn't halt. These are the 3 different outcomes for any Turing machine. But there are certain Turing machines that never loop. They either accept halt or reject halt. Those type of problems whose corresponding Turing machine accepts and halts, rejects and halts, are said to be decidable. So, if a problem is decidable, that means we have a Turing machine for corresponding to that problem that recognizes it, and it is computationally solvable. Still, in practice, it requires inordinate amount of time or memory. If you implement that using any programming language, then it will be requiring a lot of time and memory. Why this is happening? Let us get into this. We'll take a small problem. We have a language a equal to 0 raised to the power k, 1 raised to the power k, such that k greater than or equal to 0. This is a language where number of zeros followed by number of ones. A series of zeros will appear here, and then a series of ones will appear then. This is the language. We say this particular language can be decided by a Turing machine. That means a single step Turing machine. Of course, we have got different types of Turing machines, like multi-tape is there, and non-deterministic is there. So, single step Turing machine can recognize such a language, and it is decidable. It means it is halting at any cost. But we are interested in how much time it will take to decide this particular language. That is what our case is. Okay. So we have a problem at hand, and we are going to find out how it is going to decide and what time or space it will be taking. Okay. Now, if we look into this particular problem at hand, if you are given with a particular string, then what you will do? We have got steps of algorithms. The first step is we will scan across the tape and reject if a 0 is found to the right of a 1. Okay. So, what does this mean? This means that we have zeros followed by ones. Okay, zeros followed by ones. So this is a language which is to be checked whether it is decidable or not, and if it is decidable, at what time it will be decided. So the first step says that we'll scan across the entire set of string and we'll check if a 0 is found to the right of a 1. We are very particular about the position of the zeros and ones in this particular case, because the string is of utmost importance. That is why it is called as a formal language. Okay, so if 0 appears anywhere after 1, then we are going to reject it. If at all it is everything okay, as in this case everything is okay, there is no 0 after 1, so we'll repeat if both zeros and ones remains on the tape. It will check zeros are there and ones are there. So we'll scan across the tape and cross off a single 0 and a single 1. So what we'll do, we'll cross off this one, then we'll move to here, then we'll move to here, because it is a 0 will not cross off, then we'll move to here and we'll cross off, right? And then you will move to right and then you will move to right. This is what you are going to think of. So what is to be done? How you are going to decide this? Now we have crossed off 1 0 and 1 1. Okay. Now what we want that this 1 has been crossed off. Shall we move right? I don't think we should move right. We should go back again. Okay. So if we want to go back, so what we'll do? If we want to go back, so here 0 0 0 1 1 1 is here. Okay, and we have crossed off this 0 and we have crossed off this 1. Once you crossed off this 1, then what you do? Come back. So we'll come back to here, we'll cross off, again we'll move, we'll cross off, again come back, cross off, again we'll move, cross off. This is what we are going to do. This is your step 3. Cross off single 0 and single 1 at each scan. Now if zeros still remain after all ones have been crossed off, or if ones still remain after all the zeros have been crossed off, reject it. Otherwise, if neither 0 nor 1 remain on the tape, accept the language. If we follow this particular algorithm, we will see that the Turing machine will definitely stop, or either it will reject or stop or accept or stop. So hence it is a decidable language. But that is not our goal. Our goal is to find out if it is decidable, at what time it can decide it. Okay, so let us go ahead and we'll see what happens in this particular case. Okay. Okay, so we analyze the Turing machine M1 deciding A, how much time it uses. So the number of steps that an algorithm takes on a particular input may depend on several parameters. There are many parameters for this, like the input length, the memory consumed, the space consumed, right? The looping structures, all these different things are required for finding out how much time an algorithm basically takes. But for our simplicity, we are discarding certain parameters, but we only consider algorithm's runtime purely as a function of length of the string. So here, out of several parameters, we have considered only one parameter, that is basically called as the input length. Whatever length of the string is been given, that will be used to find out the runtime. Okay. Now, whenever we are finding out the runtime of an algorithm, so it will vary. Sometimes for a particular length, the algorithm will take a longer time, and sometimes it will take a shorter time. So out of all those different times of a particular length, if a string is given of a particular length, out of all the different times, if one particular running takes the longest time, then that is considered to be the worst case complexity. We are interested in this. Is it my algorithm deciding the algorithm in worst case? If that is the case, I am concerned about it. The second thing is the average case complexity. We will take the average of all the running times of the input of a particular length, and that becomes the average case complexity. Okay. Now, how we are now going to decide, define this time complexity. Suppose M is a deterministic time machine, Turing machine that halts on all inputs. So the time complexity of M is a function f that maps n to n. That means from natural number to natural number, where f of n is the maximum number of steps that M uses on any input length n. Okay, we have understood, I think. So in this particular case, what happens? The time complexity of M is the function f n to n. N tends to n. That means here input is n and the output is also n. So n domain is mapped to range, where f of n is the maximum number of steps that M uses on any input length n. Okay. Now in this case, we are going to talk about the big O and small o notation. Of course, we cannot find the exact running time of an algorithm because we have suppressed certain factors. We have taken only the input length. So hence, exact running time cannot be found out for a particular algorithm. Hence, we will take only the estimation of the running time. Now, generally what happens, one convenient form of estimation is asymptotic analysis. What is an asymptote? We will talk about it just now, but before we get into this asymptote, when my algorithm's input is very big, suppose the length of a string is suppose the length of a string is 10 to the power 6. Length of the string is 10 to the power 6. So in this particular case, how we are going to decide how much time it will take, or if that length of the string is 10 to the power 10 to the power 10, how it is going to decide? Now such a huge number, when you try to map, it cannot be plotted on a Cartesian product, and at all if you try to plot, then it will be a curve. Now finding out the area under a curve to find out how much time it is taking, it's not the convenient way. So we would like that our graph approaches towards a line. If we get lines for our estimation of the running time of the algorithm, then it will be easy for us to measure the time complexity. So in this case, what we will do, we will try to find out what is an asymptote. Okay. So asymptote is a line that a curve approaches as it heads towards infinity. As you can see, this curve approaches towards this particular dotted line, but it never meets it. So this dotted line is called as asymptote. We will be using this asymptote for this purpose. Okay. So your asymptotes can be horizontal, vertical, oblique. Okay. Depending upon your algorithm, it can be of different types. Okay. So we have understood what is an asymptote is. So it's a line that approaches, or it's a curve that approaches towards a line. Now in big O and small o notations, we consider only the highest order term of the expression for the running time of the algorithm, disregarding both the coefficient of the term and any other lower order terms. If we have got some function for measuring the running time complexity, in that particular case we will see that here we are going to disregard the coefficient as well as the lower order terms. Now why we are doing it? Because their contribution towards the time complexity is minimal or negligible, right? So suppose we are having a particular function like 5x cube minus 2x square plus 10, right? So if x is, we can take x or n, that is up to us. Okay, if x is the length of the input, suppose the length of the input is 10 to the power 20, then in this case this becomes 5 x to the power, yes, 10 to the power 20. So instead of x, I'll write down 10 to the power 60 minus 2 into, this is into here, 2 into 10 to the power 20. How I got 20? 10 to the power 20 into 2, sorry, this is 40, 10 to the power 40 plus 10. Look at this. This 10 to the power 60 is huge as compared to the rest of the things. So hence this 5, the coefficient 5, the minus 2x square term and plus, all plus 10, all these are negligible in number. So that is why we are going to disregard them. Okay, I hope it is clear. Very good. So now we have taken an example. Consider the function f of n equal to 6n cube plus 2n square plus 21 plus 45. So the asymptotic notation or big O notation for describing this relationship is f of n equal to order of n cube. So we consider this particular function will be of the order of n cube. Now why? Because we are disregarding the rest of the terms, because their contribution towards the time complexity is negligible as compared to n cube. So it is order of n cube. Okay. So we will define now big O notation. There are two functions f and g, and both f and g map from n to positive real numbers. Okay, we say that f of n equal to order of g of n if positive integers c and n0 exist, such that for every integer n greater than n0, f of n is less than equal to c of g of n. So what we are going to do here, now we have got two functions f and g which map from n to real positive numbers. We will say that f of n is order of g of n if we can find out two positive integers c and n0 such that n is always greater than n0, and if we could find then f of n is less than equal to c of g of n. So that means what we are going to do? Find out f, find out g, find out c, find out n0 and prove this inequality to be true for c and n0. If that is the case, then we say f of n is of the order of g of n, and we say that g of n is the upper bound for f of n. That means f of n cannot go beyond g of n, it will always be lower than that. Asymptotes, the lines. So the lines will be, there will be two lines, one line goes here, one line goes here, and this line will never cross the upper line, upper bound. Okay. So f of n is order of g of n, means that f is less than or equal to g if we disregard differences up to a constant. Okay. So let us take one example, the same example that we had given, 5n cube, 2n square, 22n plus 6. So in this particular case, we claim that this is of the order of n cube. The rest of the terms are being suppressed. So here f of n is given 5n cube plus 2n square plus 22n plus 6, and g of n we are claiming that it is of the order of n cube. So g of n is n cube. Now can we find out c and n0? Yes, we have found out two. These two we have found out. C is 6 and n0 is 10. Then according to definition, if c equal to 6 and n0 equal to 10, then this inequality will be proved. What is the inequality? The inequality is f(n) is less than equal to cg of n. This is the inequality. Okay, what is f(1n)? 5n cube plus 2n square plus 22n plus 6. 5n cube plus 2n square, okay, plus 22n plus 6 should be less than equal to n cube. This is the inequality. Okay, what we have to find out? Sorry, c n cube. It should be c n cube. We have to find out c and n0. Okay, now we have already found out c and n0. Okay, what is that? C equal to 6 and n0 equal to 10. Now if I use c equal to 6 and n0 equal to 10, then in that case what will happen? Now in this case what happens? This, if I put, okay, n greater than n0, so n greater than equal to n0, this is the condition. What is the condition? N greater than equal to n0, this is the condition. So I will consider the equality, so n0 equal to 10. So if I take n0 equal to 10, then n should be greater than 10. N greater than n0. If you look into this, n greater than n0. So if n is greater than n0, then I'll take n to be 11. So if I take n to be 11, then what happens? This becomes 5 into 11 to the power cube plus 2 into 11 to the power square plus 22 into 11 plus 6 less than equal to c is 6, c is 6 and into n cube, that is your 11 cube. Okay, so this inequation is true. So when it is true, we claim that this function is of the order of n cube. Okay, now for these, see, c equal to 6, n0 equal to 10. When I say n is greater than n0, n is greater than n0, n is greater than for this. I'll take n greater than n0. Now in this n0 is 10, so n should be greater than n, so I have taken 11. I can also take 50, I can also take 70, anything can be taken, so why 11? Okay, so in that case the minimum value that can be satisfied should be taken. Okay, you can take 12 also, that is not the case, because for any value greater than 10 this inequation will be true. Okay, so this is how you are going to prove it, and once you have proved that this inequation is true, then we will claim that this function is of the order of n cube. Okay, let us go to our next slide. Okay, so here some facts related to big O notation we must understand. Why we are dealing with this? We were talking about the finding the time complexity of the Turing machine, but why we came here? Because before we measure the running time of any Turing machine, we must know what mathematics behind it that helps us to understand the time complexities. Okay, let us go for this. So while using algorithms, we sometimes need to mention the base in the case of logarithms. So if you look into this, x equal to log 2n, which means 2 to the power x equal to n. This is what we know, the basic thing. Now changing the base b changes the value of log bn by a constant factor. Suppose if I mention log 2n and log 10n, so I am just merely changing any base. So if I do this, then in that particular case there is merely any extraneous changes. There are no such changes occur. Only what kind of changes occur? Only they are changed by a constant. So hence there is no need of mentioning the base whenever you are writing the big O notations with logarithms. Okay. Now we will say that f of n equal to order of log n, specifying the base is no longer necessary. So we can write down here f2n is 3n log 2n plus 5n log 2 log 2n plus 2. So we can say f2n equal to order of n log n. I have not mentioned the base, and I have taken n log n because log n dominates log n. Okay, this one dominates log n. Clear? Okay, very good. So now we will go to big O. Also appears in arithmetic expressions. Sometimes we write order of n square plus order of n. In these cases, here what happens? Some factors have been suppressed here and some factors also have been suppressed here. In that case, each occurrence of the O symbol, I mean big O symbol, represents a different suppressed constant. So in this case, f of n equal to order of n square, because order of n square term dominates order of n. So in this case also, we will consider this to be the dominating term. Some basic fundamentals related to big O notation. Okay. When big O symbol occurs in an exponent, as in the expression f of n equal to 2 to the power O of n, then the same idea applies, and this expression represents an upper bound for 2 to the power cn for some constant c. Okay. Similarly, we sometimes see f of n equal to 2 to the power O of log n, and using the identity n equal to 2 log 2n, and thus n to the power c equal to 2 c log 2n, we see that 2 of O log n represents an upper bound for n to the power c for some c. We can find out c here. So the expression n raised to the power O of 1 represents the same bound in a different way, because the expression order of 1 represents a value that is never more than a fixed constant. I hope it is clear. So we are there are certain algorithms for which we drive the bounds to be of the form n to the power c for c greater than 0. Such algorithms are said to be polynomial algorithms, or they are said to be decided by polynomial bounds. Okay, bounds of the form 2 to the power n to the power delta are called exponential bounds, and delta belongs to real numbers, and delta is always greater than 0. Okay. Similarly, we can also define the small o notation. The only difference here is this one, this less than symbol. Okay, big O notation has less than equal to, while your small o has got less than symbol. Okay, the rest are okay. So now what we'll do, we will find out some cases. We'll check whether all these inequations are true. It is a exercise to all of you. You can write down these problems and find out whether this you can prove square root of n equal to order of n or not. And if you find any difficulty, please we'll discuss. Now coming back to our time complexity measurement. Now this was the algorithm that we had given for deciding the language 0 to the power k and 1 to the power k. The language was L equal to 0 to the power k, 1 to the power k, such that k greater than or equal to 0. This is the algorithm. Okay. So we'll scan across this step 1, step 2, step 3, step 4, all the steps have been done. The same algorithm we have been talking about. Okay, let us proceed. Okay, so if you look into this, the first step, scan across the tape, reject if a 0 is found, and then a 0 found to the right of 1, then you have to reject it. So it will scan one particular array, in our case array, but in the input tape there is a, so this is my input tape, 0 is here, 1 is here, okay, and blanks are here, blanks are here. Initially your read write head is pointing to this location. Okay, so in this case what happens, we'll check that our we'll cross off each 0 and 1 in the stage 2, but in the stage 1 we'll first scan across the entire symbols to check whether 0 is after 1 or not. So this will be taking n number of, this will be taking an n time. Stage 1 can be decided in n time, correct? So stage 1 requires n steps. Now again reposition, will go to the end and then come back to the beginning. Repositioning the head at the left hand uses another n steps. So the total step is 2n. In big O notation we have order of n steps for this stage 1. For stage 2 and 3, the machine repeatedly scans the tape and crosses the zeros and ones. So at each scan uses order of n steps. Since each scan crosses of 2 symbols, so at most n by 2 scans can occur. So the total time taken by stage 2 and 3 is n by 2 into order of n equal to order of n square. Okay. In stage 4, the machine takes a single scan to decide whether to accept or reject, so it is order of n. So what is the total timing? Thus the total time of m1 on the input of length n is steps in stage 1 plus steps in stage 2, 3 plus steps in stage 4. So order of n plus order of n square plus order of n, that is order of n square. So that means the language that we have been talking about, L equal to 0 to the power k, 1 to the power k, such that k greater than or equal to 0, this can be decided in order of n square. Okay, and we know order of n square is not a good result. Can we improve this? Of course we want to improve this algorithm. Okay, so what is the, we'll see now. Okay, so here Let t is a function that maps the input n to positive real numbers in the output be a function. We'll define the time complexity class time of t of n to be the collection of all languages that are decided by order of t of n. So the language a equal to 0 to the power k 1 to the power k belongs to time of n square, because m1 decides a in time order of n square. Okay. Thank you. And how to improve this particular algorithm we will talk in the part 2. This is part 1, and for your information, all these are the different functions that you will be requiring to measure the time complexity of a particular algorithm. So this is order of 1 or n, and this will be log n, this will be order of n, this will be n log n, n square, and n factorial. So here input is there, here time is there, and this is your asymptotes. Okay. Thank you so much for listening to us. We'll meet again in the part 2.